I made this video yesterday. If you saw that, it got messed up. I don't know what happened. Anyway, here we are. I have a previous video that I showed that if you have an object orbiting halfway around the Earth or tunneling through the center, they get to the other side at the same time. That was kind of fun. I liked it. It's a good problem. But it assumed the density of the Earth was uniform. What if the density of the Earth is not uniform? I tried to model that in the previous video and failed, so now I'm going to do it right. It's going to be great. I know I can get it to work because I already did it. I already made this video, and now I'm doing it again. But I'm going to rebuild it for you because I think it'll be fun, and I'm going to have fun. Even though I already did it, I'm still going to have fun. So here's where we are. The main idea is that I can calculate the gravitational field due to some object like a planet. And once I know the gravitational field G, I can calculate the gravitational force, the mass of any object I put there, multiplied by the gravitational field G. Now, according to Gauss's law, which I'm not going to derive, but it is true, that if you go inside the Earth, if I'm at some point inside of the Earth, like right here, then the only mass that matters for the gravitational field is the mass that's closer to the center of the Earth. All this other stuff does not contribute to the gravitational field. I mean, it essentially cancels. All this, the gravitational field due to all these masses cancels at that point, so you only have to worry about this stuff right there. So, I already have a model. I'm going to show it to you in just a second. The key here that I'm going to do, I decided to build this in 3D so that we can see it. I'm going to go ahead and show you the model, which I just said that twice, didn't I? I did. Okay. I'm just excited to finally get this thing to work. So what I'm going to do is calculate the gravitational field, but the mass that I use to calculate the gravitational field is going to be a function of the position of the object. So I have this model. So far, all I have is an object orbiting, which doesn't depend on the changing mass. I'll just put the mass of the Earth in here. Let me show you the code, and then we'll come back here and see how to fix it. So here is the computer, and let's make this much bigger. Big, 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 big. Is that good? I think that's good. So what do I have? That's the radius of the Earth. That's gravitational constant. This is the mass of the Earth. This right here is the density if the Earth is uniform. So I just took the mass of the Earth divided by the volume of a sphere. I'm going to use that in my first model. This is the radius of the core, density of the core, density of the outer side. And then in order to calculate the mass in between that core and the surface of the Earth, I just find the mass of the core right there. It just turns out to be easier for me, and we'll use that in a little bit. Now I have the Earth and the core. I just made them as 3D objects. I made a ball, and it's at the surface of the Earth, and it's going to orbit around, so it has a mass of 1, which doesn't matter. I calculated the vector from the center of the Earth to the center of the ball, which you don't technically need since the Earth's at the center, but I did it anyway. Here I calculate the velocity needed to orbit around the Earth. And then I have the momentum of the Earth. No, that's the momentum of the ball. Mass and velocity, there's that. It's moving in the y direction. I did rotate the Earth. So the Earth starts off with the northern hemisphere, the North Pole at the top. I just rotate it so that we're looking at it from the top. I don't know why I did that. So then I have a time step of 2 seconds. And then I'm going to let the ball orbit until it gets back down to y equals 0 again, because it's moving in the y direction. So it's just half an orbit. Rate just tells you how fast things go. I recalculate R1 because it's going to move. G1 is the gravitational field, right? So I calculate the gravitational field. It's just negative G, mass of the Earth, and then I have to use the unit vector R1 divided by R1 squared, and that's fine. F1 is the gravitational force. It's just M times G. And then I update the momentum, update the position, update time. Let's run it. I'm kind of excited because I think this is pretty fun. So I made the Earth partially see-through so you can see the core and so you can see the orbit. Because if you look at the Earth like this, straight on, then you really can't see. If you zoom out, you can see it. But the object is so close. It is on the surface of the Earth. So you couldn't really see it. So I did that just so you could see things better. But it rotates around the Earth, and that's that. Okay. Let's build a model where I calculate the mass. So what I'm going to do is to build a function. I'm going to call this function m. And this function m is going to calculate the mass depending on the location. I'm going to assume a uniform density Earth because I know the answer to that. And then we can make it to a non-uniform. So up here, I'm going to make a function. Let's put the function right after let's put it right here. Right here. Okay, so if you haven't used Python functions, they're pretty awesome. I'm not a great functioner. I make mistakes when I make functions. I do them in the non-best way. That's what I mean to say. Some people may say, hey, that's not a good idea. You should behave and do the rules the right way. But at the end of the day, I think the most important thing is that you feel comfortable making a function, even if it could be a bad idea for more complicated programs. There, I said it. So let's make a function. I'm just going to add it right here. I'm going to say def, that's how you start it, m, that's the name of my function, and then I need to tell what variables am I going to pass to that function. I'm going to pass to the function just the variable rt. Okay, so rt is my temporary position. I'm going to pass a position, a vector position, and it's going to return a mass. That's all it's going to do. And we can see how this works. Now, I already have the gravitational constant. I already have the density. So I already have all that stuff. It's a global variable. I don't need to have them in here. Although some people would say you totally should do that. And I totally didn't. Because again, I want to make fun functions. So what I'm going to do is to take that temporary position and I want to say, okay, is that inside or outside of the Earth? If it's outside, so if mag RT is greater than R, if that's the case, then my mass is just going to be the mass of the Earth. So I'm going to say return. This returns the function. It's going to return me. That's just the mass of the Earth. And me is that. Okay, that's rho. I just wanted, I don't know if I have that exactly the same. That's fine. Okay, I know I had the mass, looked up the mass of the Earth, and then calculate the mass of the Earth based on the density. And this one, I calculated the density based on the mass of the Earth. I thought I did it before. Oh, here I did it down here. I'll do that one. I'll do this one, turn that one on later. Okay, so if you're outside of the Earth, the mass of the Earth is the mass of the Earth. But what if you're inside? Well, I can say else. So if you don't meet that if criteria, then we're going to do the else. And I'm going to calculate the mass. It's going to be to calculate the mass, it's going to be the density in kilograms per cubic meters times the volume of the enclosing sphere. So it's going to be, let's just say return, the density, rho 0, that's my density, times the volume, which is going to be 4/3, times pi, times mag RT cubed. Mag RT is the radius of my sphere, right? And that should work. So now what I need to do, down here, when I calculate the orbit, I use me. I'm going to use m of r1. Right? So I'm going to pass it the vector r1. It's going to give me back the mass. Now I start at r, the radius of the Earth, so it should be fine. Down here, also when I recalculate the gravitational field, I'm going to say mr1 instead of m. And that's it. Now, I'm not going inside the Earth, so it should work just fine. Let's just see. It's just do the same thing it did before because I didn't really change anything. Okay, so it is indeed orbiting. Looks good. Now, let's add a second ball. I'm going to add a second ball, and this ball is going to start and just fall through the center of the Earth. And it's a uniform density Earth, so they should get there at the same time. Let's just copy all this. Copy. Paste. And now I'm just going to change this to ball 2. The position's the same, the radius is the same. Let's make it cyan. And then I'm going to say ball 2 mass. I need to calculate R2, ball2.pos, V orbit. I don't need. I'm just going to comment that out. Ball2.p, the momentum. Yeah, I am using the momentum update formula here, just so you know. I didn't even go over that, but I assume that you'd be okay. And it's going to start with a momentum of 0. Now down here, I need to do the same stuff I did, but I need to do it for ball 2. So I'm just going to copy all of that stuff. and paste it. Oops, paste. And then I'm going to change these 1s to 2, 2, G2 is going to be MR2, R norm R2, mag R2 squared, 2, F2. See, it's not hard. Just change stuff. 2, 2, one more. I got to do these positions to start over here. 2, 2, 2, and 2. Now let's see if this works. So I should have one ball orbiting like I already had, and the other one should just be moving through the center. They should get to the other side at the same time. Let's see if they do. Nice. Okay. So there we go. There's our orbit. And the thing is that's nice here is I did this in 3D. It gives me a picture. And before the mistake I was making was that I had trouble calculating the gravitational field, but also giving it a direction, right? Because if I just confine this to the x-axis, then the gravitational field is pointing in the negative x if it's in the positive x direction, but the positive x in the negative, and I messed that up. I know I messed that up. Okay, so now let's go over to the paper. Let's think about how we can change this function for a non-uniform density Earth to make sure we got that working. Okay, so now let's say that I have right here, I have really 3 regions I need to calculate the mass. So I have if, let's just say the vector r is greater than r, then the mass is going to be equal to the mass of the Earth, which I already had. Now, the next case, I'm going to be if I'm in this region right here, so I'm going to say, let's put a little line there, if R1 R. So if it's in between those 2 regions, then the mass is going to be equal to the mass of the core, right? All of this stuff, plus the density, rho 2, which is density over here, times this volume. So this volume is going to be equal to 4/3 pi r cubed minus r cubed, right? Because it's a shell of a sphere. So I have to take the volume of the whole thing, which is going to be in here. So that's just r cubed. No, this should be backwards. A good thing I wrote it. This is going to be r cubed minus r1 cubed. Right? Because I don't care about the other stuff. It's going to be from here to there. So I'm going to take the volume of that sphere minus the volume of the inside sphere, and that will be my volume. And then finally, if r is less than, not r, if r magnitude is less than r1, then m is just going to be equal to the density rho 1 times the volume, 4/3 pi times r cubed. Okay, let's put that into our Python code and see what happens. Going back to the function right here. Okay, so this part right here is fine. If that's true, that's fine. Okay. Now, let's say that's not true. Let's say that's not true. Then in that case, I'm actually going to add another if. And so you got to be careful with multiple if statements, but this will work, right? Because if it gets to that, I'm pointing at the screen. If RT is greater than R, it's going to return ME and it will be done, right? Oh, and I'm going to go up here and recalculate ME, right? So this is the mass based on those 2 densities because I just picked some densities and I want to calculate the total mass and to have them the same. So that's going to be my new mass of the Earth. That's fine. Now, if the next thing is going to say, well, if it's greater than R1. So I'm going to say if mag RT is greater than R1, then it's inside the Earth. It has to be because it didn't get this one right here, but it's greater than R1, so it's in that region. So then I can just say return MC plus 4 times pi divided by 3. That's at 4/3 pi r cubed times, and what did I say? the mag RT cubed minus R1 cubed times the density times rho 1. Yeah. Now I can do else, and then this is for inside the core, and this is going to be rho 1. This is rho 2. I'm sorry. I called that rho 2. Rho 1. Yep, that should do it, okay? So if you think about how it's going to go, if it gets greater than R, fine. Otherwise, it's going to be greater than R1, fine. Otherwise, it's inside. So it's kind of a weird if, else, but I think it works. I think that's all I had to do. I think let's just run this and see what happens. Because I already have that function down here. I guess I should save this, at some point. And I will give you the link to the code. Do not worry about that. Okay, so they did not get there at the same time. Notice that the one that goes through, I call that ball 2, actually got there first and started coming back. I set the loop based on that orbit, so they're not the same. That's exactly what I thought. So if the Earth has a non-uniform density, it takes less time to fall through. If this is assuming that the density of the core is higher. Because what's happening here is during this part right here where it's falling, there's a very large mass in the middle, so it has a large gravitational field. This is going to create a larger acceleration during this phase. And then once it gets inside, it won't increase as much, but it already sped up. And then the reverse happens on the way back. Let's go ahead and plot. This is what I wanted to make before, remember? Let's make a plot, G1, of the position of the x position as a function of time for both of those objects. So G1 is graph, title equals fixed Earth tunnel. You can make up any title that you want, it doesn't matter. X title equals time, and I'm going to put this in minutes just for fun. Y title is going to be equal to x in radius of the Earth. I'm going to, just because it'll look a little bit better. I'm going to do that. And then let's put the width equals 400, height equals 250. And now I'm going to make, that makes my axes, right? I need to make my functions to plot. F1 is G curve, color equals color dot blue. And then let's put a label. Label equals orbit. F2 equals G curve, color equals color dot red, label equals tunnel. Now, down here I'm going to plot those two things. Let's just plot them after the time. It doesn't really matter. So I'm going to say F1 dot plot. I want to plot T, but I want to put it in minutes. So I'm going to divide by 60 because I'm calculating the time in seconds. So if I divide by 60, that gives it in minutes. And then I want to plot the x position of ball 1. So ball 1.pos.x. And I'm going to divide by r, which is the radius of the Earth. I said I was going to have it in radiuses of the Earth. And the same thing for 2, plot t divided by 60. Ball 2.pos.x divided by r. Let's see what happens. And there you'll see the tunnel one gets there first because of the difference in densities. Okay, now there is I used a 2 density model for the Earth, right? I said the core has 1 density and it's uniform. The outer has 1 density and it's uniform. And the Earth is not like that. It actually has multiple levels, and each level isn't exactly constant. So if you wanted to, if you look up density of the Earth, you can build a better model and plot that. But I want to do one more thing. Let's try something else because I want to show you something fun. What if I go up here and I go for ball 1? Ball 1 right here. It starts off with a orbital velocity. It goes in a circle. I calculate that based on forces. So what if it's not going orbital velocity? What if it's going slower than orbital velocity? Let's say 0.8, so 80% of orbital velocity. So it's not going to orbit. If that's the case, it's going to actually dip into the interior of the Earth, and that gravitational field will change. Let's just see what happens. What happened? We almost went. It didn't quite make it. Let me make it a little bit slower. Run that 70%. Let's go a little bit slower. I think something seems weird because I did this before and it was much more dramatic. 60%. So there might be an error in my code. I'm feeling a little less confident, but I'm happy. Okay, that's good right there. So you'll notice that this one stopped. The cyan one stopped because my loop is based on this other orbiting one, and it does not make it to the surface. So what about energy? If you think about the tunnel one, it's going to go through there and come back to the same point, and the change in energy would be zero, right? Because it had a change in kinetic energy and a change in gravitational, and it didn't lose any energy, so it got back up here. But if that's, and it got to the other side, same thing. But this one doesn't get to the other side because, one, it's not orbiting. Two, at this point right there, it's not stopped. It's still moving. So the sum of the kinetic plus potential right here is the same as it is over here, even though it's further away. So that's why it doesn't quite make it to the surface. If you let it run a longer time, it should make it back to the surface over here. Let's do that. Let's do that real quick. I feel like I'm going to break stuff though. Let's do while t is less than 2,000 seconds. Let's just run it for 2,000 seconds and see what happens. That might not be enough. I'm just guessing. Oh, wow. What a guess. Let's do 4,000 seconds. Oh, well, is it not going to get back to the same point? It should. I thought it should. Huh. That one did. The other mass is working. This one is just acting weird. I'm not sure what's wrong, but remember, one, the audio's working, so that's good. Number two, the point was to show what happens when you have a non-uniform density, which I did that. So there may be a problem here. I'm going to look at it. You can look at it too, but that's that. Okay. I'm going to give you a link to the code. I'm going to give you a link to the previous video, the one that worked audio-wise, but not calculation-wise. I hope you enjoyed that.